So welcome to today's session of the Discrete Maths Course 2. Well, this also marks the beginning of the second half of the course. Believe it or not, we are already in week 7. Seems crazy. Time flies. Life is a bitch and then you die. And on this word of hope, let's get started by doing something very interesting. Today, first of all, we are going to wind up our brief discussion of the inverse of matrices. And then we start on a topic which I hope you will find really interesting. It's supposed to be highly motivational for you. So I'll do my best to continue motivating you. We're going to look at functions that map vectors to vectors. And these functions will take two forms. There will be functions induced by matrices, and they are also known as linear functions. This is a very interesting topic, so I hope you will have all your spider senses tingling. So as usual, before we start with the new stuff, let's warm up. Let's get our neurons buzzing by answering a few questions. The reason why I'm asking these questions is in fact multifold. The main reasons are, first of all, we want to warm up. Second, they allow us to refresh some of the old material by doing it in the best possible way, namely by thinking about it and trying to answer some questions about it. Finally, when you prepare for the exam, you can refresh your knowledge of the material by going back to all these questions and answering them. And they are there, all collected under lectures. So there we are. There are 3 questions today that I would like you to answer together with me. The first question asks, okay, suppose I give you a matrix, and this matrix has m rows and n columns. What is the largest rank that this matrix can have? And I encourage you and also the people at home to think aloud. Well, for the people here in the lecture room, I will listen to what they think aloud. For the people at home, it would be a little bit more difficult to do so. But think aloud anyway, with us. Okay, some people are saying M. Okay, so there is a suggestion from Elisa, I believe. Is that right? Fantastic. I know at least one of the students. Well, don't ask me. I guessed. No, not really. I didn't guess. Okay, she said it's the smallest value between m and n. Now, why does this make sense? Let's try to think aloud. First of all, what is the rank? In order to answer this question, Moses said, "Thou shalt know." That's the first commandment. Thou shalt know what the rank is. And the rank is the number of leading ones in the reduced matrix associated with A. Now, you can have at most a 1 per row. So you cannot have more than m ones. On the other hand, a leading one corresponds to a variable. So for instance, if you have 3 rows and 2 variables, how many leading ones can you have at most? Well, as many as the variables, isn't it? So the maximum rank that you can have is the minimum value between m and n. So that's what I mean by thinking aloud. That's exactly what we've been doing, thinking aloud. And convincing ourselves that what we are saying actually makes sense. If you cannot even convince yourself that what you're saying makes sense, most likely it doesn't. But that's a good start. Before you start convincing someone else, convince yourself that what you're saying actually holds water, as they say in the UK. Question number 2. Are there any questions about question number 1? This sounds like recursion, and it is, but we stop here. Okay, so to think about it at your leisure, the rank is the number of leading ones in the reduced form for A. Well, how many leading ones can you have at most? Well, you can have at most one per variable, but you can have more than one per row. So the smallest number between the two has got to be the largest rank. Question number 2. Suppose that you take your matrix A, and in the reduced row echelon form, there is a row that reads 0, 0, 0, 0, line 2. Which conclusion can you draw about the associated linear system of equations? Inconsistent, one of your friends said. And that's absolutely right. Why? Because this says 0, 0, 0, 0 means give me a linear combination in which everything is 0, the result should be equal to 2. Well, that's not possible, is it? There is no way that 0 times x can be equal to 35. Well, of course, the number 35 is chosen as an example of what a b can be. Oh, in this case, or 2. In the algorithm that we looked at, namely the Gauss-Jordan algorithm, there was a line that said, if at any point you have a row that says 0, 0, 0, 0, 1, then you're inconsistent. Then you're inconsistent. Well, here you have a 2, but you can just divide the whole row by 2, and you get a 1. So that's the situation that we know about. Any doubt about this? Hopefully not, because this was more basic than the previous question. If not, you know what to work on, which is another reason why we ask this question, so that we figure out what we need to work on a little bit more. Question number 3. Do you have the answer? Okay, so let me read the question aloud, because sometimes reading the question aloud actually answers it. Well, let's see whether that's true in this case. Assume that you have, again, the reduced row echelon form, and you have a row that says zeros everywhere. Can you draw any conclusion about the associated linear system? Okay, the question is this at the bottom? Well, actually, it's not a question. It's a statement. The row must be at the bottom of the matrix. And that's absolutely right, because we are looking at the reduced row echelon form. In fact, in any row echelon form, all the 0 rows are at the bottom. But does it tell us anything about the number of solutions of the associated linear system of equations? Doesn't it depend, or the question is, doesn't it depend on how many equations there are? Yeah, I guess it might very well do. It doesn't really tell us very much by itself. In fact, we cannot really draw any conclusion. So, for instance, you could have another row above which looks like the one that spells inconsistency, or you can have a matrix which is the identity matrix. In that case, you have a square matrix. In that case, you only have one solution. Or you may possibly have infinitely many solutions. So basically, anything goes. It doesn't really tell us anything. The only thing we can say is, as your colleague said before, is that this row must be in the lower part of the matrix. There could only be zero rows there. But this per se is just a purely syntactic criterion. It doesn't tell us anything about the number of solutions. So sometimes people think, okay, as soon as I have a 0 row, infinitely many solutions. Well, wait a second. It depends. You have to look at what else you have in your augmented matrix. Okay, are you warmed up? I can hear the neurons buzzing in your heads. Mine are already fried, but yours are still buzzing and alive. That's how it should be. So now that you're ready, let's look at the scary slide. In fact, that's not scary at all. It lists a bunch of properties of an operation that we mentioned last time. Okay, I realize it can be a little bit scary. But I think your friends in the lecture room will explain what this says for us, and we will explain it to all of you at home with a joint effort. What is it that we finished by doing last time round? We introduced the notion of an inverse of a matrix. Now, when is a matrix an inverse of another one? Okay, one of your colleagues down there is saying a sort of a matrix A, a matrix B is an inverse of matrix A if the following is true. The inverse of A if A times B equals B times A, and this is the identity matrix. Now, for what type of matrices is the inverse well defined? Where rows and columns are the same numbers. These are the so-called square matrices. And really, square means it looks like a square. It has n rows and n columns for some n. So it's a two-dimensional array where you have the same number of rows and the same number of columns. Fantastic. So basically, the inverse of a matrix is like the inverse of a number. If you have a number A which is non-zero, 1 over A is the inverse, because if you multiply the two, you get 1. In this case, the role of 1 is played by the identity, because every matrix multiplied by the identity remains itself, doesn't change. Splendid. Now, we may ask ourselves, what kind of properties? Oh, by the way, we also saw how to compute such a matrix if it exists. How do we do it? By using what? I can hear the neuron buzzing here in the lecture room. By using the linear algebra calculator toolkit. Yes, we could do that, but what is the linear algebra toolkit using? It's using the elementary row operations. Okay, so you want to figure out the inverse of a matrix A, you form an augmented system that starts like this, where I is the identity matrix. Then, whoops, you use the row operations, and you want to get something like this instead. If you can do that, if you can turn A by using elementary row operations into the identity matrix, then on the other side, by magic, which is not magic, it's because you're solving a system of linear equations, well, a bunch of linear equations simultaneously, then after the solid line, you will get the inverse of A. This can be proved, but I'm not going to do this to you. I'll just give it to you as an algorithm that someone else showed works. In fact, this has got all to do with the fact that elementary row operations solve a systems of linear equations, and you can solve them simultaneously. So that's how you do it. If you can do that, then you get the inverse. And we saw some examples last time round. So far, so good? In fact, you can do it if you really want. So the question I want to ask now is, what kind of properties does the inverse have? For instance, suppose that I know that A is n by n and is invertible. Invertible means it has an inverse, and this inverse is written a to the minus 1, like I said before. Just like for a number, a, small a to the minus 1 is 1 over a. That's the inverse. Okay, and suppose I have another matrix, B, which is also n times n, and it's invertible. And its inverse is b minus 1. Question. Is the matrix A times B invertible? What do you say? Okay, so one of your colleagues is saying yes. And what would the inverse look like? Okay, of course he knows because he's also following the linear algebra course at the same time. I know where you live, so jokingly, no, I'm just, but in fact, that's right. And let's see why this works. And this will also show you this apparently odd feature that you actually turn the multiplication the other way around. Okay, so this is A times B, but the inverse is B to the minus 1 times A to the minus 1. Why is that? Okay, so first of all, let's check whether this works. Okay, so one thing that we want is that A times B times this thing here should be the identity. Okay, why is that? So this is a useful exercise because it also refreshes our memory of some properties of the operation of matrix multiplication that you should know and love from an earlier course. So does it matter how we bracket this multiplication? In other words, can we actually write this multiplication in a different way without forgetting about all these brackets? Matrix multiplication is associative. This means that it doesn't really matter how we bracket this thing, so let's forget about the brackets. We can multiply this thing in any way we like, and we get always the same result. Oh, sorry, the minus 1. You know, whenever I see ABBA, I start forgetting about the minus 1s. Otherwise, they spoil the name of the band. Okay, so can we simplify this expression? Yeah. Okay, so look at this part, the underlying blue thing. One of your colleagues is saying, well, B minus 1 is the inverse of B. So B times B minus 1 is what? It's the identity. Beautiful. So we can replace the B times B minus 1 by its result, which is the identity. Now this has become Aya, AI, A minus 1. But what is I, sort of A times the identity? It's just A, because that's what the identity does for you. It's like 1 in multiplication. Anything multiplied by the identity of the appropriate size will just give back A. And now what is it that we have? We have again the identity because A to the minus 1 is the inverse of A. So multiplying AB by B minus 1 times A minus 1 gives us the identity. And you can multiply also the other way around, and you will also get the identity by following exactly the same line of reasoning. It's just that first you have the A matrices and the A minus 1 next to one another. They disappear, turn into the identity, and the pattern is exactly the same. So what is it that we found out, thanks to your colleagues in the audience? We found out that if you have 2 invertible matrices, when you multiply them together, you get an invertible matrix. And in fact, we know how to calculate the inverse of a multiplication of A and B from the inverses of the multiplication of B and A by applying this multiplication, this formula that we have before. Okay, so what other properties are there? So this, by the way, is property 3 on the slide. The property 4 is, well, it's just a generalization of this property that works for any number of matrices you're multiplying. So if you have 35 matrices, they're all invertible, you just do this trick, but you get 35 matrices, inverses that you want to multiply in the opposite direction. Now let's look at property number 2. Property number 2 says that if you have an invertible matrix, then its inverse is also invertible. Well, no surprise, it's the matrix you started from itself, which is the inverse of its inverse. So this is like not of X is equal to X. In Boolean logic, it's exactly the same principle. And you don't really need to prove anything here, even though I'm foolish enough to do that. So the definition of an inverse is just this. Well, this definition tells you that A minus 1 is the inverse of A, but it also tells you that A is the inverse of A minus 1. You just swap the role of the two. So the inverse of A minus 1 is actually A. That's what this tells us. So far, so good? Any question? Okay, this looks like it's very boring, judging from the faces that I am facing right now. Come on, guys and gals. This really makes your life simpler sometimes. So let's look at the last row, and then I let you read the rest at your leisure, and we move on to something that will really sort of make your juices flowing. Okay? So suppose that I have that A is invertible, then we can look at something which is called the transpose of A. Question to you. You knew I was about to ask this question. Also for the people at home, pause the recording now and refresh your memory of what the transpose of a matrix is. I know it was a previous life when you saw it, but still, you saw it. What is the transpose? Yep, you basically turn rows into columns and columns into rows. Now, the relationship between inverse, so I think people want an example. They haven't asked for it, but I'm going to give it to them. So if I have my matrix A, which is, well, whatever. What is the transpose of this? Some people are saying it's the same. Why? Because this is a symmetric matrix. It's exactly the same. I turn rows into columns, but the matrix was symmetric along the diagonal. So if instead I take B, which is this thing, what is the transpose? The same. It's symmetric. The transpose doesn't change. If instead I take the matrix C that looks like this, what is the transpose? So this is the entry, which is at position 2, 1. This becomes the entry in the transpose at position 1, 2. In general, when you're doing the transpose, if you have an entry at position ij in your matrix, this will go to position ji. That's the rule for forming the transpose. So if you take, say, a two-dimensional array, you want to build a transpose of it, well, that's easy peasy. You just apply this rule at all of the entries. Yes? Oh, well, the question is, what does the arrow mean? Sort of, it just means goes to. So if this is C, position ij goes to C transpose, becomes the entry. Oh, you shouldn't read too much. It's not a functional arrow. We haven't started the part about functions yet. Just goes to becomes. Allow me to be informal sometimes. Okay? Did you see the transpose at some point in your previous lives? I guess so. Fantastic. So, what is the message? The message is that not only inverses can be efficiently computed, they have lots of nice properties that relate them to the standard matrix operations, in particular with multiplications and transpose. The important properties of the inverse operation are summarized really here on this slide. So you don't have to remember them all. In fact, you don't have to remember them. You just need to use them whenever it is useful to use them to simplify expressions that have to do with matrices. Just like you use the standard rules of multiplication, summation, and whatever other operation you love to simplify expressions you having to do with times, plus, and whatever else you need to simplify. Okay? I want to see a little bit of fire in your bellies, guys and gals. Come on. You're here to participate in this wonderful intellectual opportunity, which is the one where you teach me something. That's how it goes. Now, in order to complete our discussion of inverses, let's connect once more computing inverses of matrices with something that we've been doing over and over again, namely solving systems of linear equations. Not only can we compute the inverse of a matrix when it exists by applying the elementary row operations, which are our tool to solve systems of linear equations, but the existence of an inverse tells us something very special about the number of solutions to a system of linear equations associated to the matrix we are trying to invert. And this is encapsulated by this result here that says that if we have a system of linear equations, here A is the matrix of coefficients, X is the vector of variables, x1, x2, xn, equal to some constant vector B, then this will have a unique solution if and only if the matrix A is invertible. And if the matrix is invertible, you can find the unique solution simply by multiplying the vector B on the left by the inverse of the matrix A. Isn't this cool? And why is that? Well, your colleagues here in the room are saying, easy, don't even show it to us. But you know, I mean, I'm just doing it for myself, not for you. Okay, so this is the equation we want to solve. Now, of course, this only makes sense for square matrices, because otherwise we don't have an inverse. Okay, suppose A is square and A is invertible. Okay, so how do we find the solution vector X? Well, since A is invertible, there is a matrix A minus 1. And we know how to compute it even. But somebody has computed it for us. Here it comes, A minus 1. Welcome. We just need to use it. So how do we use it? Well, we can multiply both of the sides of these equations by A minus 1. So we get A minus 1 times A times X should be equal to A minus 1 times B. But hey, what is this? That's the identity. So that's I. I times X is equal to A minus 1 B. But what is I times X? It's just X. So actually, the only X that solves this equation is the vector that you obtain by multiplying A minus 1 with the constant vector B. So if you pick this X, you surely solve the equation. And moreover, that's the only X. There are no other X's if the matrix is invertible. If the matrix is not invertible, then, well, either you have infinitely many solutions or no solution. But bear in mind, this connection only applies to square matrices, because otherwise the notion of inverse is not defined. So there you are. Inverses are also useful for solving certain systems of equations. So there you are. If somebody tells you inverses are not useful, well, tell them you don't know what you're talking about. I was trying to solve an equation and an inverse came along, it solved it for me. So it's useful. In fact, we will see, if not today, on Thursday, that inverses also are closely related to some properties, so some nice functions that we can define using matrices. And this leads naturally to the next topic in the course that we are going to deal with, which is the topic of functions taking vectors to vectors. So what I'm going to do now is to introduce for you the notion of vector that we're going to work with today and on Thursday. And afterwards, we take a break, and then we will look at functions. Now, for those of you who don't like inverses, it's time to wake up. Because now we are going to look at functions, which is something that you write all the time whenever you write programs, isn't it? Perhaps you don't call them functions, you call them methods, procedures, whatever. But if they return a result, they're really a function of the input parameters. So the functions that we are going to look at are functions mapping vectors to vectors. And these functions are actually at the core of lots of computer science applications. For instance, what is happening right now on the screen is linear algebra, functions. Well, we're just saying nothing is happening on the screen. Yeah, yes, something is happening. My slide is being projected on the pixels there. With the colors, not very many, but there are colors there. There are points where there's something written down, points where there's nothing. How can we represent this? Well, by using linear algebra in some form of primitive computer graphics. And sometimes I want to do stuff with this. For instance, I want to shrink my images, my pictures. How is it done? Well, LaTeX does it for me, but why? How can it do that? Well, there's linear algebra inside, shrinking and enlarging. So all of these pictures are represented by means of very high dimensional vectors. Now, what are vectors? Vectors are exactly what you think they are. They are one-dimensional arrays. When you're doing linear algebra, these are one-dimensional arrays of numbers. In the course so far, these numbers are real numbers, but they could be complex numbers, or to make it simpler and more palatable for us computer scientists, they could be zeros and ones. Now, if you want to sound cool, then these zeros and ones, there will be elements of something which is called GF2. Now, what does this mean? Well, this means that the operations over bits that we are going to consider are AND for multiplication and exclusive OR for summation. Note, not OR, exclusive OR. And the reason why exclusive OR is nicer than OR is because every bit has an inverse, a uniquely defined inverse if you're doing exclusive OR. Whereas this is not true if you're doing OR. For instance, the inverse of 1 is 1 because it gives you 0 with respect to plus, exclusive OR. But anyway, so I will tell you later about why this GF2 stuff, bits with AND and exclusive OR, are so nice in computer science. But for now, let's think about real numbers. Let's pretend that we are mathematicians. Okay, so what is a vector? As I said, it's a tuple of numbers. In fact, whenever we are doing vectors over real numbers, this is the notation that we use. Rn is the collection of all n tuples of real numbers. That's because the Cartesian product R times R forms pairs of numbers. R times R times R forms triples of numbers. In general, R to the n, R times R times R n times forms n tuples of numbers. That's Cartesian product. And some of these things you've known and loved from high school. R2 is the set of points in the Euclidean plane, in the Cartesian plane. We will draw them later on. R3 is the set of points in the Euclidean space. R4 is in space-time, but we are not going to go there. In general, we can deal with Rn, but are never going to draw anything beyond 2 dimensions. That's already difficult enough for me. Now, before we break, let me introduce you to the object that we are going to study for a couple of course sessions. Namely, the notion of a transformation from n-dimensional vectors to m-dimensional vectors. What is this? Well, that's nothing but a function that maps n tuples of real numbers to n tuples of real numbers. And since they are functions, we write t of x for the result of applying the transformation t, the function t, to the input vector x. Let me give you an example. So let's look at functions from pairs of numbers to pairs of real numbers. Well, that's an example of a function. Give me a vector xy, I will give you xy. Boring, isn't it? Give me an input, I'll spit it out. That's the so-called identity function. Okay, here's another example. Let me call it T1 to distinguish it from the other one. Give me a vector, x, y as input. I'll give you the vector 0, 0 out. I don't even look at your input, I spit out 0, 0. That's a function. It's boring, but it's a function. It's a transformation from pairs of numbers to pairs of numbers. It's a constant function. That's the so-called zero function. Okay, one more example. Perhaps slightly less boring. Give me a vector xy. I will return the vector where I've doubled x and I've left y unchanged. This was x after Christmas. X ate too much, doubled in size and in weight. Whereas y didn't eat, and so it stayed the same. Or at least it ate a normal amount of food. That's a transformation. That's a function. So for instance, if we feed this function with the input 1, 1, it will return what? 2, 1. Yeah, that wasn't a trick question, was it? It was just me not wanting to do the calculation myself. Okay, so nothing new under the sky. These are just functions, but they're functions from vectors to vectors. What we are going to do after the break, and this is the trailer so that you can really look forward to something during the break, what we're going to see afterwards is what kind of functions can we define in terms of matrix multiplication? What properties do this function have, and can we characterize them? And make no mistake, these are going to be very special functions, but the fact that they are very special is a good thing, because even though they are very special, they have wide applicability. For instance, in topics like computer graphics, coding theory, the transformations that code and decode pieces of information can actually very often be implemented in terms of matrix multiplication, which is something that we can do efficiently. Okay, so that's the trailer. Now we take a break. After the break, we will study transformations in more detail.